Today we're going to focus on Unit 4, Lesson 2, Gravity in the Solar System. Your standard is 622. Recognize that gravity is a force that keeps celestial bodies in a regular and predictable motion, holds objects to the Earth's surface, and is responsible for ocean tides. What is gravity? Gravity is something we've already studied this year. It's a force of attraction between objects due to their masses and the distances between them. Every object in the universe pulls on every other object. Objects with greater masses have a greater force of attraction than objects with lesser masses have. You've already learned this. You and a sumo wrestler jump out of a plane. The object with the greater mass will have gravity's greater attraction, so the sumo wrestler will be pulled on more by gravity. Something we haven't really talked about this year so far is that objects that are closer together have a greater force of attraction than objects that are farther apart. So two things closer together will have a greater gravitational force than objects that are farther apart. Gravity is the weakest force in nature, yet is one of the most important forces in the entire universe. And that is because it accounts for the formation of the planets, the stars, and the galaxy. That means gravity accounts for how the planets, stars, and galaxies are formed. Gravity also keeps smaller bodies in orbit around larger bodies. And an orbit is defined as the path a body follows as it travels around another body in space. So, for example, the moon is a body that orbits the Earth because it follows a path around the Earth. The Earth orbits the sun because it follows a path around the sun. What are Kepler's laws? First, before we can talk about Kepler, we have to talk about some other astronomers. The first one is the 16th century Polish astronomer, Nicholas Copernicus, who changed our views of the solar system. He discovered that the motions of the planets could be best explained if the planets orbited the sun. Like astronomers before him, Copernicus thought that the planets followed circular paths around the sun. However, Danish astronomer Tycho Brahe used special instruments to accurately measure planetary motions over a period of 20 years. Using Tycho's data, Johann Kepler, this is where Kepler comes in, discovered what we call Kepler's laws of planetary motion. So this brief history lesson shows you how science, the learning never stops. What's started by one astronomer is continued by another and another until we get here to Johann Kepler. Upon plotting the orbit of Mars, Kepler saw that it wasn't a circle. It was more of a deformed circle. And after 8 years of work, he realized that it was not a circle at all, it was more of an ellipse. Kepler then proposed that each of the planets had an elliptical orbit, with the sun at one focus of the ellipse. This elliptical orbit is what we call Kepler's first law. So the discovery that the planets have an elliptical orbit is Kepler's first law. When an object follows an elliptical orbit around the sun, there's one point, called the aphelion, where the object is farthest away from the sun. So you think of A as not, as a root word, right? Not, or as a prefix, A meaning not. So not close to the sun is how you can remember that. There's also a point called the perihelion, where the object is closest to the sun, so next to the sun. Today, we know that the orbits of the planets are only slightly elliptical, but the orbits of objects like Pluto and comets are highly elliptical. Kepler found that a planet moves slower at its aphelion, remember that's farthest away from the sun, sweeping out a narrow sector on the ellipse. Conversely, Kepler also found that a planet moves faster at perihelion, remember that's the point where the planet is closest to the sun, sweeping out a thick sector on the ellipse. As a planet moves around its orbit, it sweeps out equal areas in equal times. This is Kepler's second law, equal areas and equal times. Kepler also looked at how long it took for the planets to orbit the sun and at the sizes of their orbits. He discovered that the square of the orbital period is proportional to the cube of the planet's distance from the sun. This is very technical jargon. I don't expect you to remember that. But the square of the orbital period is proportional to the cube of the planet's distance from the sun. This is Kepler's third law. We'll look at this again in a minute. What is the law of the universal gravitation? Using Kepler's laws, Sir Isaac Newton became the first scientist to mathematically describe how the force of gravity behaves. He thought that gravity is a force that accounts for both the fall of an apple from a tree and the movement of the moon around the earth. In 1687, Newton formulated the law of universal gravitation. The law of universal gravitation says that all the objects in the universe attract each other through a gravitational force, something we take for granted today, that all objects attract other objects, but Sir Isaac Newton was the first to discover that. And look, it's a law. That means it can't be broken. It's something in science that always happens. The strength of this force depends on the product of the masses of the objects. Gravitational force is also inversely proportional to the square of the distance between the objects. Lots of math here, guys. How does gravity affect planetary motion? If a ball is attached to a string and is swung around, it moves in a circular path. The inward force that causes the object to move in a circular path is called centripetal force. If the string breaks, the ball will move off in a straight line. When the string is intact, the centripetal force prevents the ball from flying off. If you've ever ridden on the giant swings at an amusement park, you've felt a centripetal force. Also on roller coasters that have those tight curves, those turns that go around, you've felt a centripetal force. When planets orbit the sun, a force similar to the centripetal force prevents them from moving out of their orbits and into a straight line, so that keeps them in their orbit. The sun's gravity is the force that keeps them moving around the sun. So if you imagine holding a ball on a string and swinging it above your head, your hand is the sun in our solar system, and that ball would be a planet going around the sun, because the sun's gravity is what's keeping that centripetal force going on. Collapse. How did the solar system form? The formation of the solar system is thought to have begun 4.6 billion years ago when a cloud of gas and dust collapsed. This kind of cloud from which solar systems form is called a solar nebula. In a solar nebula, the inward pull of gravity is balanced by the outward push of the gas and pressure of the cloud. Scientists think that an outward force, perhaps the explosion of a nearby star, caused the nebula to compress and contract under its own gravity. The solar system formed in a single region of the nebula, perhaps several light years across, and the sun probably formed from a region that had a mass that was slightly greater than today's mass of the sun and planets. As a region of the solar nebula collapsed, gravity pulled most of the mass towards the center of the nebula, and the nebula contracted. It began to rotate with increasing speed, and then it flattened out into a disk, and that disk is called a protostellar disk. That's where the central star, our sun, was formed. As the protostellar disk continued to contract, most of the matter ended up in the center of the disk. Friction from matter that fell into the disk heated its center to millions of degrees, resulting in the fusion of hydrogen atoms into helium atoms. And the process of fusion, remember we've talked about fission is when atoms break apart. Fusion is when they're coming together. That released large amounts of energy, and the gas and dust stopped collapsing, and the sun was born. As the sun was forming, dust grains collided, they stuck together, they formed granules, which increased in size, and the collisions between these bodies formed larger bodies called planetesimals, from which planets were formed. So planetesimals are small particles that were crashing together until finally it became large enough that planets were formed. The protostellar disk became the protoplanetary disk in which the planets formed. The inner part of the protoplanetary disk was so hot that only rocks and metal were in solid form. The collision of the rocky planetesimals and the inner disk led to the formation of rocky metallic planets. We call these planets the inner planets or the terrestrial planets. Earth is a terrestrial planet. In the cold outer disk, massive planets made the icy and rocky planetesimals may have formed. The gravity of these planets was so strong that they captured gas and other matter as they grew. Therefore, these outer planets have rocky or metallic cores, and deep atmospheres of gas and ice. They're called gas giants. Things like Neptune is a gas giant. Uranus is a gas giant. Here's a picture of the planetesimals, the sun and the center being formed. Okay, now you need to please fill out a visa and make sure you get a signature, and be ready to show me in class tomorrow your